Tomasz Łuczak for the first time. He was still young, very talented mathematician. And it was about the time when he also received the prize of the European Mathematical Society. He also became the youngest member of the Polish Academy of Sciences. Presently, his affiliation is in Adam Mickiewicz University and Emory University. And today he will talk about his probably favorite topic, which is the evolution of random graphs and in particular threshold functions.
Thank you very much for such a kind introduction, and overall thank you for the invitation. So it's a great honor and privilege to speak at the conference, which is dedicated to Paul Erdős. So usually we start with some sort of personal memories of Polibachi. So let me just show you one photo, which I got from Ehud Friedgut. So this might be the last photo of Paul Erdős. It was taken in Thai restaurant in Warsaw, near Banach Center, a few days before he died. So I had to leave Poland and go to Emory 2 days afterwards. And I remember when I came to Emory, I entered the office of Wojtared, and he asked me, "Have you heard about Paul Erdős?" So I was convinced that Paul Erdős made to Atlanta before me. And I said, well, no, I thought he will stay in Warsaw for some more few days, but then Wojta told me the bad news, and then I knew that some important period of my academic career ended at this moment. So you may feel some melancholy in my voice. This is because I participated in quite a few conferences celebrating Paul Erdős' birthday. And I'm afraid this is the last one. Certainly there will be another one celebrating Erdős' 200th anniversary. But I might not be so active in this area 100 years from now, so I'm afraid I will not get an invitation. Anyhow, what I would like to tell you is some sort of historical survey of one of Paul Erdős' favorite area. So let me start with the photo of Paul Erdős' diploma, which was given on the occasion of giving him honorary degree of my Poznań University. So it is probably hardly readable, so I just wrote down the most important parts. And in Latin, it's quite convenient. It's very hard to write something in Latin. But if you see it, it's very easy to understand it. So if I read you qui in arte combinatoria and grapharum et theoria numerorum auctoritatem toto orbe terrarum maximum adeptus est, everybody roughly knows what's going on here. But what we will be especially interested in is this mention that he is one of the co-founders of theory of random graphs. By the way, I contacted my friend who is a very well-known trained classical, who is trained in classical literature, so he assured me that both graph and random was made up by the guy who translated this diploma. So now I understood why we learn about Euclid and Archimedes, and we don't hardly any Latin mathematician, because they lack basic terminology to have advanced mathematics. They don't have the word graph in Latin. Anyhow, so let me start with some definitions. So probably you know both definitions of random graphs, and I will be mainly, but not exclusively, dealing with these two basic models. So one is the binomial model, when we have n vertices and we choose an edge with probability p independently for each potential candidate. And another definition is the uniform. Another model is uniform random graph when we choose a graph at random from among the family of all graphs with n vertices and n edges. And you must remember that these graphs are random objects. So what we consider is just the family of graphs with some probability measure on it. And I mentioned, I wrote up the measure. So in GNP, basically every graph can potentially appear as GNP with a positive probability. In GNM, there are only graphs which has m edges, and they appear with the same probability as GNM. They should be GNM here, and as the second line, of course. So the main theme of this lecture are threshold functions. So here's the definition from the classical Erdős-Renyi paper. So the function of n, and it also depends on a given function of p, is a threshold function for property A. If the graph is such that if we generate this graph GNP with probability larger than this threshold function, the probability that it has this property tends to 1. And if the probability is substantially smaller, then the probability tends to 0. And as you probably remember from the talk of Bella, Erdős and Renyi defined these threshold functions for GNM, and they denote it by gamma nm. But basically, we will use these two models interchangeably. And they called it just threshold function. But for some reason, I will call it such type of thresholds Coles thresholds. So here is an example of the threshold, probably the best known example. So this is the threshold the threshold function for the property that a random graph contains complete graph on R vertices. And it reads, what we can read off from this statement is that this threshold function for this property is of the order n to minus 2 over r minus 1. But by the way, the threshold function, you need to remember that threshold functions are given only up to a constant at these coarse threshold functions. And it's quite surprising that, so the natural question is, what happens when we replace this kr by some other graph? And the answer depends what graph you mean. So for cycles, for instance, it was already done by Erdős and Renyi. And the argument can be repeated for every graph which is so-called balanced. But in general case, it was done only by Bela-Bolobash in 81. He found coarse thresholds for every graph, for containing every graph H. And so now we enter this early period of random graphs, and these were really nice times, because basically what we were doing at that time is just to choose, we pick up our favorite property, we try to guess what is the threshold function, and we try to prove it using first moment method and Chebyshev inequality, basically. So how we guess the threshold function, basically there were two standard ways of doing it. First way was to find a necessary local condition. So sometimes proper global property depends on local condition. And sometimes we just compute expectation of some random variable. And look when this expectation tends to infinity and when it tends to 0, then it should be, we should detect the threshold in this way. So the first threshold which was found using this local principle is connectivity threshold, found already by Erdős and Renyi back in '59. And if you just look at this threshold, it is another type of threshold as we talked before, because there are two functions. So there are two terms in this threshold. So the first term is, the second term is responsible for the behavior of the probability, and the leading term is just the term which roughly tells you in which place is the threshold. And such a threshold is called a sharp threshold function, and as a matter of fact, the terminology is also due to Erdős and Renyi. So another important threshold function which was found based on this local principle is Hamiltonicity threshold. So we consider property when graph is Hamiltonian, and I just mentioned this threshold, and there are several reasons for that. First, to show you that this field was highly competitive even at that time. Secondly, this is the first time, and I think this was Bella who introduced it, when we defined the threshold using so-called heating time. Because GNM can be viewed as a state of Markov chain. So we can obtain GNM instead of selecting it uniformly at random from the family of all graphs with n vertices and m edges. We can start with empty graph and add edge at randomly edges one by one. And what we get as the m stage of this process is precisely GNM. And what Bella proved, and independently it was done also by Komers and Semeredy, they proved that if we look at this process, first time the minimum degree of this graph is 2, then we have already a Hamiltonian cycle. And in fact, GNP can be also considered as a state of Markov process. Now the time is continuous. And the last reason I would like to mention it is because basically, I think this is a sort of milestone. This result ended some early period of random graph theory. So starting from '83 and '84, there were many results which were much more complicated. So, for instance, there was the famous phase transition result of Bella. And in '85, Bella's book appeared on random graphs. And there were quite a few quite sophisticated methods. But we will go to that. Let me just go back, if I can do that. Okay. So as I told you at the very beginning, it was easy game. So we tried to pinpoint all possible thresholds. So if you just look at it, it immediately is clear that the hardest thresholds to find would be the one which do not depend on local properties, and for which we cannot, it is not easy to compute expectation. So there are two seminal examples of such behavior. One was the question when the graph can be colored with k colors. So it was done much later by Bella and by myself. But the first ones who can compute expectation of the number of colorings, and in this case it was the second moment of the numbers of colorings, was only Arctioptras and Naor in 2005. Another property is the Ramsey property, and you might heard about it. So this is a property that if we color a graph with two colors, say, there is a triangle there. So it's very hard. So first of all, it does not depend on any local structure. Secondly, it is almost impossible to compute the expectation of such colorings. So we don't know how to do it right now. Anyhow, Red and Luczynski did it without expectation. This was much more complicated argument, but the subject is still alive, and if you heard the conversation of Ehud Friedrich, Paul Herder, and Socrates, you know that a lot is going on even now in this area. So, can we have some sort of general theory of thresholds? So first of all, a simple observation that every monotone property has the threshold. And by this I mean that if the threshold, if the probability at some point is larger than epsilon, then if we multiply the probability by a large constant, it will be larger than 1 minus epsilon. And here is the proof. So this is a very simplified statement of what Bolobaj and Thomason proved, and here is the proof. So this graph Gn Kp is roughly the union of k independent copies of Gnp. And this is basically all you need to know, because then the probability that Gn Kp has A is bounded from above by this expression, which by choosing k large enough may be made arbitrarily close to 1. But there were two other attempts of so what you need to observe is that this simple argument does not depend on the property A at all. And we would like to have a theory which classifies the properties. So there are two questions. First, given a function, Pn, can we decide if this is a threshold function for some property? And the question number two, suppose that we are given property, can we decide whether the threshold for this property will be sharp or not? So let me look at the first question. And the first question is concerning 0-1 lows. So this is what people were doing about in the 90s, and now this is almost a dead subject, but maybe it can be survived, as we will see briefly. So here's the main objective. Take a class of properties. And what you would like to know is for what functions the probability that Gnp has this property tends to 0, 1. And what does it mean, favorite class of properties? Typically, we characterize this class by the language in which we describe properties. So the most popular choice was first order theories. So these are properties which can be described by quantifying only over vertices, not over a set of vertices, for instance. So you cannot define connectivity. Connectivity is not the first order property. The property that diameter is 2 is the first order property. And now let me just tell you very quickly about the art of proving such stuff. So, so basically the standard approach was we need to find the complete system of axioms. And for graph series, first order graph series, there are nice, at least for some series, there are nice complete system of axioms. So the system of axioms is completed. For each formula we know, we can deduce this formula or its negation from these axioms. And then we show that each axiom holds almost surely. So this was basically the technology, and here is an example of the result. No threshold function has this coefficient irrational, basically. So if we have a probability which is n2 minus alpha, and alpha is rational, any property tends to either to 0 or 1. So you may ask what happens when alpha is rational. And surprisingly, the things here are more complicated. So let me just give you examples, a quick glimpse of kind of results you can get. Suppose that Pn is close to n2 minus 1, 7, but Pn is strictly less than n2 minus 1, 7. So then there is such a function for which 0, 1 low holds, but for every function which is recursive, 0, 1 low does not hold. So this is the types of wonders you can step on when you are dealing with 0, 1 lows. But let me quickly go to the other question. The other question is, suppose that we look at the property and we would like to decide whether the threshold is coarse or whether the threshold is sharp. So first, let me look at two properties. So the first property is that the graph has a triangle, and the second property is the connectivity threshold. So what is the difference in these properties? And the major difference is the following. If you are near the threshold, so near the threshold of the connectivity, the graph consists of large component and some isolated vertices. So if you add an edge, and this edge with large probability will be in the largest component, you know, for the triangle, it creates possible places to close the triangles which did not appear before. So it's so every edge near the threshold on the left picture is relevant. So the property very strongly depends on adding of each edge. Of course, for the largest component, the probability does not change at all. And it turns out that this characterization of the property influences the fact whether it has sharp threshold or not. And of course, even if we think about it, it's not quite clear whether it helps to have a sharp threshold and this does not. But in fact, it can be made precise using harmonic analysis. And here is a meta-theorem which was proved by a number of very distinguished authors. So it says that if A has a sharp threshold, then basically all minimum graphs which has this property A are small. So basically, it's these properties which have sharp thresholds depends only on having minimal graphs which have this property. And furthermore, if thresholds are sharper, these graphs can be made much smaller, and there are some upper bounds of the size of this critical family, and it helps when the property A is highly symmetric. So this basically, as I said, it's very hard it would be probably pointless to define it rigorously. But let me just mention some names. So I think the subject was started by the paper of Kahn, Kalai, and Lignon. But then it was taken over. First, there was this continuous version by Bourgain and Katz-Nelson and three guys who are doing the first paper. And then there is this, you see, the nice combinatorial structure because we have three authors and all pairs appear as the pairs of co-authors. The last one is a bit cheating because, but let me just put it this way. And the bounds for the sharpness, which follow from general theory, are usually a sort of logarithmic. So one wonder how sharp natural thresholds can be. And furthermore, does it really matter? And sometimes it matters how sharp is the threshold. For instance, if you have a property that the graph contains a subgraph which has more edges than vertices, then the width, so how sharp is the threshold is a sort of fundamental question because it determines the width of what is called the phase transition window. So at least at this particular case, we do care. So let me just finish this part of the talk with two remarks. First one is that there is no theory. There is no theorem which says for every first order property, so first order properties cannot have thresholds like this. So you have a sharp threshold, but maybe is it possible that this exponent here is irrational? We don't know. Nobody really ever worked it out. And second question, which is also quite fundamental. Suppose that you have a sharp threshold. How sharp can be the threshold? And it seems that the properties which has the sharpest threshold are the properties a graph has more than a given number of edges. But this is really the case? We don't know. This is not the case in other models. For instance, the cluster scale model, but let me just skip it. And let me go back to the random process. So as I told you, this graph the graph GNM can be viewed as a state of Markov chain. And there are some properties which you can define for random graph process, but which doesn't make any sense for GNM. And one of the favorite properties of poor Erdős is the properties which is related to the so-called race of components. So suppose that we have this random graph process, and we add to graph edges one by one, and at some point we see the largest component. So you wonder, if you add edges, whether this largest component will be overcome by some other component. So maybe there are two smaller components will join together and will be larger than this component. And the time, so this random variable is the time we should wait until the largest component in GNM will be overcome by some other component in the graph. And of course, this random variable doesn't make any sense when we don't look for the process. And here is one of the theorem of Erdős. So it turns out that for every n, this time, we can, for no m, we will wait more than n over log n. And basically, it's sharp. But then there is a wonder. So if you take the maximum of this, there is an extra log n factor. You may say, well, these two theorems contradict one another. But the point is that we put it asymptotically almost surely, which means with probability tending to 1, in different places. So the first statement tells you the following. If you just give me a function n, and I start with look at the process at this function, and I look at the first moment the largest component will be overcome, then I need to wait at most n over log n time. But maybe I have the whole film. So I film all the process, and I look through all the frames, and I choose the frame when this distance is the largest one. Then there is an additional log n factors because I choose among many such cases. Because basically the component switches a lot of times. So this is basically an iterated logarithm time result. So let me just recall you what is the law of iterated logarithm. If you flip a coin, usually the difference between tails and heads is of the order square root of n. But if you just look at the maximal difference up to the time n, there is an additional log n factor. So the difference is of the square root of n, but there is an additional log n factor if you do this. Okay, so I can wonder. So I was wondering. So we have this log n. So is it possible that by putting this asymptotically almost surely at the very end of the statement, we gain a factor which is larger than logarithmic? And there is one chance of doing that. So here's this is the model of bootstrap percolation, but maybe I skip it as well. And let me just jump to the, because Vera Schoch in his opening lecture mentions that we shouldn't be concentrated only on the past, but we should look at the future of the subject. So I was just wondering what is the future of random graph theory, in which direction we can go. And I think there are two directions which look very promising. One is geometric and the other is topological. So let me just tell you something about random groups. This is a geometric direction I would like to recommend. So I will, let me just recall what is the presentation of the group. So S is the number of generators and R is the number of relations. So basically this group is the group of words with letters from this alphabet, which is the generator. So with letters A1, A2, these are the elements of S, and maybe the inverses of these elements. And R are the special words which we consider to be empty. So we can put this, any element of R inside the word, and we can cancel it, and so on. So here is a quick example. If we have a group which have two generators, and this is a relation, this relation just means that AB is equal to BA. So two generators commutes. So this group basically consists of this type of words, because we can order them. So this group is basically isomorphic to Z2. And another example, if we have three generators and one relation, but the C, one generator, appears only in one relation, we can compute this C and replace this C in any word by expression involving A and B. So this is basically the same as this free group with two generators. And this is a geometric operation. And this is called Titsemu, whatever it means. Let me just emphasize that basically this is a very geometric statement, because if you have a presentation of the group, this group is the fundamental group of a very natural object. And note that both of these examples are infinite. So now we go to the random group subject. So in 80s, Gromov, as a matter of fact, in early 80s, Gromov proposed to define random groups using their presentation. So here's the model of the group. We have K generators, and we choose this set of relation among all words of length L. But we don't choose all of them, and the number of the words are basically controlled by this density. And the density is in exponent. So this is the parameter which will control density, and in Gromov model, he decided to take only finite number of generators, but the length of the word went to infinity, and he considers the asymptotics of it. And there is another model, which is Zhuk's model, which is quite popular. So now the number of generators goes to infinity, but we take only the words of finite length. And here, why I think this, oops, I'm sorry. So it will be a challenge to finish this lecture, unhearted. But anyhow, so here, why I think this direction is promising, that's what Gromov said back in 80s. So he said that random groups theory is basically very similar to random graphs. And note that the definition of the random group appears in 1980. And I told you about the first period of random graph theory. So it lasted about 25 years. So you may hope that at this moment something interesting is going on in random group theory, and basically this is about what this corresponds to real situations. So let me just tell you something, for instance, about the known critical densities for random groups. So first question is, when if you have enough of this relation, the group will collapse to a trivial group. So what density you need for that? And the density is 1/2 for both Gromov and Zhuk models. It appears to be universal. And the other interesting property of the group is so-called Kazhdan property, which I will not define here, but it's extremely important. It corresponds roughly to the property that a graph is a good expander. As a matter of fact, there are deep relations between expander groups with the Kazhdan property. So it's not known for Zhuk's model, but we have no idea what is the density for the Gromov model. So we know that the critical density is between 1/5 and 1/3. And now you can guess what is the most likely value of dt. Apparently, recently it was conjectured it's 1/4. But what I tell you is critical density, and you remember this d controls the exponent. So all these thresholds are much more coarser than the coarse threshold for random graphs. But you can, in the very same way, ask what is a sharp threshold for some of these properties. And there are only few which are known. And some of them can be obtained quite easily, but some of them require some more insight, both combinatorial and algebraic. So you wonder whether there are some sort of 0-1 laws. So for instance, are there densities which are critical for some group properties which are irrational? But nothing like this is known, which is quite surprising. So if you just look at the model series and you look at the vita of any known model theory, groups are basically the objects they like best. You always have something about groups. So you may say, well, okay, maybe this problem is very hard. So it is, for instance, known that if you have, in general, if you have a presentation of a group, it is undecidable to decide whether the word is an empty word, if you are given just a presentation. But this is not the case with random groups. So all random groups are almost surely hyperbolic. And hyperbolic groups were basically invented as a groups for which there is a Dane algorithm which decided whether the word is non-empty or not. And in hyperbolic groups, you can decide it in basically linear time. As a matter of fact, this Dane algorithm is a very nice algorithm which just gives you the group, and the Dane algorithm translates the problem into some tessellation of hyperbolic plane. So this was a really nice idea, and Dane algorithm was invented just at the beginning of the last century, 1905. So you see that the groups are really have a very strong geometric flavor. So for the last few minutes, I would like to go to the other topic, which is topological, and which is probably a bit easier to explain. So the main idea is that we just generalize random graph into random hypergraph. But when we look at it, we consider properties which are topological properties. So we generate this hypergraph, and maybe we complete this family of sets by all subsets. So this is a simplicial complex. And we will consider properties of this complex which can be defined using topological language. So here is an example of theorem of this type. So this is a theorem of Babson, Hoffman, and Kahle, which was proved just a few years ago. So suppose that we have this complex, and we consider the fundamental group of this complex. The question is whether this group is trivial. And it seems that this So they prove a threshold which is not really a very sharp threshold, but maybe this is close to be the case. So the critical exponent is minus 1/2. And by the way, there are many geometric extremal problems, for instance, of Eridge and Schoch, to mention one which are not known, but this is a sort of random setting. And what you need to notice is that this exponent, minus 1/2, after which the group collapse, is very similar to the exponent, to the critical density in Gromov groups. And it might be that this is not a coincidence. So there are many people who try to either deduce one result from the other, or try to prove a sort of general result, from which these two results will follow as a special case. So once again, these Gromov groups are fundamental groups of some object which was constructed in a random way. And in this construction, we use critical density 1/2. And here, we have a random graph in which the density is 1/2 as well. But let me just not comment more on it, but instead show you some other property. So instead of this random hypergraph, I will look at the matrix. So the incidence matrix, but the incidence matrix which looks in the following way: rows correspond to subset of size k, and columns correspond to the subset of size k plus 1. So the maximal subsets, the one which we chose at random, are labeling columns. And the other subset, the subsets which are by one smaller, will label the rows. So for instance, this is a matrix which has a random size because the number of columns are basically the number of hyperedges in this graph. So for instance, this, in the one-dimensional case, this matrix is nothing else but the incidence matrix of GNP. So here we have vertices which corresponds to row, and columns corresponds to edges. So here is another example. So this is two-dimensional one. So this is our random simplex. So we have two columns. One is with blue and one is green. But we have 6 pairs of vertices. So for instance, the last row corresponds to this pair of vertices. It belongs to no triangle. And the first row corresponds to this pair of vertices. It belongs to both. And there are 2 questions which we would like to consider. One is question of vanishing top homology. But it can be stated without invoking topological notation. So we need to find the threshold such that we would like to know that if we take any subset of column is independent, basically. So the first dependency appears, then the top homology group will not vanish. But if all columns are independent, then the top homology will vanish. So here is a short dictionary. Homology means we look at the dependence of columns. If we look at the dependence of rows, it would be cohomology maybe. Top homology means that the rows of the matrix are labeled by this very large simplices. So we have these columns which are the maximal size simplices, and the rows are labeled by the second largest size subsets. And there's a question of collapsibility. So when we will be sure that all columns are independent? Well, if the matrix has the following property. Anytime we take a subset of columns, we'll find a row in which there is only one non-zero entry. obviously, there cannot be any dependence in such set. So collapsibility implies vanishing of homology group. So let's look how it, let's translate this into one-dimensional case. What does it mean for graphs? So dependence of columns means dependence in, I should say, in the field of size 2. So we are in Z2. Is a threshold function for the property that G and P will contain a subgraph with all degrees even. This is precisely the definition. And the question on collapsibility is, oh, I'm not quite sure, maybe it flipped on. So is the property that there exists a subgraph with all degrees larger than 1. And if you think for a few seconds, these two properties are equivalent. These two properties just tell you that the graph contains a cycle. So the threshold functions are the same. But this is not the case for larger, large dimensional simplicial complexes. So let me just mention some results and conjectures. So different subsets of this set of authors. So if you see, there is Nati Ligal and there is Roy Meshlam, who used to be a Nati student, and there is a PhD. Lior is a PhD student of linear. I'm the only black sheep in this group. So, so we prove the following. First of all, we can find the collapsibility threshold, which is not so easy. Secondly, it is easy to see. So, we proved that basically, if you look at the matrix, and the matrix is roughly rectangular, there is no local dependence among the columns. So if you would like to have a subset of columns which is dependent, you need to take a substantial number of it. So this is the second property. And for the third one, we are not sure. We would like to prove a sharp threshold for this vanishing of top homology. And every evidence we have and every conjecture we have shows that for K, which is at least 2, this threshold appears much later than the threshold for this for collapsibility. And there are some applications of this results. One possible application is in the theory of codes, and you can, if you know anything about the theory of codes, you easily recognize the application. If we have a parity check matrix for error correcting codes, basically what we would like to know is that there are no local dependence among columns. The smallest set of columns which is dependent give you the distance of the code, basically. So when I was preparing this talk, I realized that I am pointing out new directions. And so the natural question emerged, well, if Paul Erdős would point out in the same direction too. And for a moment I have doubts, because I talked to Paul many times, and he never asked me, for instance, take a random simplicial complex, what homology groups are torsion-free? But then I realized that Erdős was a very polite man. He never asked a question to anybody who would not understand it. And at that time, I would have no idea what he is asking about. But now, we have this new generation of young combinatorists who are much better trained in general mathematics than I was at that time. And Paul also learned very quickly. So I think he would gladly ask this question to some young mathematicians here. So probably the response would be, okay, Paul, but over which field we are doing this? Homology over which field? And Paul probably would smile and answer, Z2, Z2, I am really an old and stupid man. And probably he would add some jokes about stupidity and his old age. But certainly he would be very satisfied with the conversation with another young absolute. So this is what I would like to put. Thank you.
Thank you very much. We have some time for questions. So,
So two comments. One, regarding a question that was on one of your slides, is it true that the sharpest threshold is for graphs with a given number of edges? The answer to that is yes. That is known. So if you write the expression for the derivative of the probability, it turns out that all graphs with more edges than the expectation give a positive contribution to the derivative, and all graphs with smaller number of edges give a negative contribution to the derivative. So to maximize the derivative, you just take all the property of having all graphs with more than the expected number of edges. So that's one thing I wanted to point out. And the second remark I have is regarding what you said about in your final few sentences. I don't know if Vera is here. So maybe Vera can give a better description. But I believe that Vera and Erdős and Brown had a paper that dealt with finding when a sphere appears in a 3 hypergraph. So actually your prediction is true. He was interested in this.
Yes, I know that there is this beautiful conjecture from this paper about extremal number of triangles which force torus, I think, which is still open. But Paul hardly mentioned homology group. So, but maybe just because my stupidity. That's what I would like to point out.
Okay. More questions?
This is more a comment to Ehud's comment that, of course, I don't doubt that you're right about the derivative of the function, but as a probabilist, I prefer to see that result that the number of edges gives the sharpest threshold by saying that if you take G and P model, you can think of that as the mixture of G and M. You have a random number of edges, but if you condition on the number of edges, you have exactly G and M. And then it is easy to see that the threshold for number of edges is the sharpest one. Every other threshold is somehow smoothed out. So you can see it in different ways.
So, I would like also to ask a question. So you mentioned these applications in coding theory, so that there is this big open problem of the dependence of the rate on the distance of the code. So do these results go in the direction?
Unfortunately, we cannot beat the best bound.
But
this is a very natural way of generating error-correcting codes. And furthermore, we don't really study this model so well. So we are at the beginning of the road. So for instance, we have no idea how to prove this threshold for the homology group. But of course, the collapsibility threshold doesn't give it.
But so it is conceivable that it may lead to such results like improving upper or lower bounds.
Well, maybe it's too early to predict.
More questions? If not, then thank you very much, and we have break.
Logarithm is